Hey, hi there and welcome back. This is part 2 of air pressure and wind. We'll talk about some physics here, and first we'll talk about the pressure gradient force, and then we'll talk about the Coriolis force, and then we'll talk about the friction force. But let's start with the pressure gradient force. And again, all of this is very well described in your textbook, chapter 5, pages 97 to 103. Pressure gradient force, you can think of the difference between popping a tire and popping a balloon. So keep that in the back of your mind as we step through this. Now, we talked about this in the first section here. The pressure gradient force, if you will, forces air to blow down the pressure gradient. You can always imagine high pressure areas as a hill of air, if you will. Lots of air molecules piled up. You can always imagine a low pressure area as a pressure hole, if you will, or an area of less air molecules. And the air is basically flowing down this pressure hill, from the pressure hill into the pressure hole, the same way water would flow down a hill. And that air flowing down the pressure hill from high to low, that's wind. That's the same thing that happens when you pop a tire. There's high pressure inside your tire. There's lower pressure outside of your tire. When you pop a tire, what happens? The air rushes out. The air basically flows down the pressure hill from inside your tire to the outside of your tire. That's wind. Here's another weather map that has, if you will, two pressure hills. One here, and a whole bunch of different pressure lows. So air is flowing from this hill, down the hill into the low, from this hill, down the hill into the low, and so on and so forth. So a weather map always shows you the pressure hills, the high pressure areas, and the pressure lows, the gaps of air, if you will. And the same way water would run down a hill, air runs down the hill. All right, now, the only thing now we have to think about is how steep that hill is, right? And that's a function of the pressure gradient, and that's indicated by how tightly these isobars are bunched together. So for example here, they are very tightly spaced. They're very close to one another. That means the hill from high to low is pretty steep, and there'll be pretty strong winds blowing. All right. Conversely, in this part here, there's a fairly wide gap between adjacent isobars. That means the wind is pretty weak. So, here's the summary. The pressure gradient force essentially forces the wind to blow down the pressure gradient from high pressure areas to low pressure areas. The wind speed is determined by the pressure gradient, and you can see that on the weather map by the spacing of the isobars. So you can think about air as a skier. A skier glides down the hill. A skier will ski fast when the hill is steep, and the skier will ski slow when the terrain is flat. Well, same with wind. Or you could think about air being like water. Always water flows straight downhill. It flows fast when it's steep. It flows slow when it's flat. Your weather map shows you the hills of air, if you will, and shows you the holes of air. And air flows from the hills, down the slope, down the gradient into the lows. And you can just play that game pretty much with every weather map. Here's another weather map. Here's a schematic, right? High pressure. Air will always flow down this pressure hill. And it'll flow fast down the pressure hill here, where the isobars is closely spaced. It'll also flow this direction, but much slower, because here you have a much wider spacing between the isobars. That might be the difference between popping a tire and popping a balloon. You pop a balloon, it's pretty mellow, because the pressure difference from the inside of the balloon to the outside of the balloon isn't that great. If you pop a tire, yeah, you got a much bigger pressure difference, so it's going to be a much louder bang. You can play this game now. You can look at a weather map, and here we have sort of a simplistic weather map, a schematic weather map, and you can draw in the wind direction because of the pressure gradient force, and you already know how to do this, right? So think about this for a second. Draw in the wind direction. due to the pressure gradient force. And you kind of have a little cheat diagram here off on the side. So, well, you can stop the recording and think about this yourself, but we're going to go on, and bam, there they are. The pressure gradient force forces the wind to blow from highs to lows down the pressure gradient. The wind blows perpendicular to the isobars. Wind speed is proportional to the pressure gradient. Right? So here, for example, high pressure, low pressure is over here. Wind blows from high to low, blowing down the hill perpendicular at a 90-degree angle across the isobars. And you can look at every one of these arrows. They will all go from areas of higher pressure to areas of lower pressure, and they will cross the isobars at a 90-degree angle. They will go perpendicular to the isobars. That's the pressure gradient force for you. You can play the same game on a real weather map. Here's a real weather map. You don't have to be a fancy weather person on TV to figure this one out. You can do the wind prediction. They use the same rules as we do. Right? Rule 1, winds go from high to low, perpendicular to the isobars. Right? High wind speeds you get from a high pressure gradient, and you see that by a close isobar spacing. Low wind speeds require a low pressure gradient and a wide isobar spacing. So you look at your weather map and you figure out where are the highs, where are the lows, right? Where are our isobars, and then you draw in the wind direction. If you want to do that, you can hit the pause button, otherwise we'll go on, and there we go, right? High pressure here, wind is blowing down the pressure hill perpendicular to the isobars. Here's a low pressure hole, if you will, so the wind blows into this hole, crossing the isobars at a 90-degree angle. Highest wind speeds will be down here in the Gulf of Mexico. Why is that? Because see how tightly these isobars are spaced? That means you have the steepest pressure gradient and you have the fastest wind speeds. Here's another example. Where are the high pressure areas? Where are the low pressure areas? And then look at the isobar spacing. So think about this and mentally draw in the wind direction and the wind speed. If you want to do that, hit the pause button. Otherwise, we'll go on, and there we go. We have a big, big, big hill of air over the middle part of the country, these high pressure areas. And we have a huge hole of air, if you will, over New England. So all the wind rushes down the pressure gradient, flowing at a 90-degree angle across the isobars, rushing down the hill into the hole, if you will. So there you have it. That's the pressure gradient force. Unfortunately, and that's highly unfortunate, that's not the end of the story. We have to also account for the Coriolis Force. And that's what the handout is for. I have a dedicated handout that explains the Coriolis Force to you. Right? Yeah. You can also watch this YouTube video. Yeah. So, let's talk about the Coriolis Force. There's 3 ways we can do this. And it's handled on page 100 to page 102 in your textbook. You can either memorize facts, 4 facts in fact. You can use a lot of equations, or you can sort of do plan B, and that's what we're going to do. We're going to try to figure out what happens on a rotating Earth. Right? We're not going to use the equations. We're going to memorize and use plan B. So, there we go. Here's a fact. Fact number 1, the atmosphere and the oceans are not glued to the Earth's surface. Thus, the Earth, if you will, rotates underneath the Earth's surface, underneath the atmosphere and the oceans. Therefore, winds in the northern hemisphere are deflected to the right as they blow from high to low pressure areas. Winds in the southern hemisphere are deflected to the left as they blow from high to low pressure areas. The same thing applies to ocean currents. The same thing applies to anything traveling in the atmosphere or the oceans. Whether that's a bird flying, a baseball flying, a rocket flying, a ship, a duck swimming on the pond, a fish. Anything that travels in the atmosphere or the oceans in the northern hemisphere is deflected to the right as it travels. Anything in the southern hemisphere that's traveling in the atmosphere or the ocean is deflected to the left. That's just a fact of physics. So when you watch that video, you're going to see Doug Flutie throwing his famous Hail Mary. As that football was airborne, as that football was in the air, it was being deflected to the right. Fortunately, over these short distances, the effect is minimal. So when the pitcher throws the baseball, the deflection is minimal until it reaches the batter. But if something travels over hundreds or thousands of miles in the atmosphere of the oceans, the deflection becomes really relevant. So let's look at this. Here's a classic example. Imagine you're standing at the North Pole and you're firing a rocket to New York City. Now, as that rocket is airborne, let's say it takes 10 minutes to fly from the North Pole to New York City. But as that rocket is airborne, of course, the Earth continues to rotate. Right? So if you're just shooting straight down, the rocket will crash somewhere in the Midwest. The path of the rocket is deflected to the right relative to its sense of motion. Because basically, as the rocket is airborne, the Earth rotates and New York City rotates eastward. Consider what happens when you stand at the South Pole and you shoot a rocket straight northwards. Well, as that rocket is airborne, the Earth will rotate, right? The Earth rotates here from left to right. And your rocket will crash somewhere in the Pacific Ocean. The path of the rocket is deflected to the left relative to its sense of motion, because now we're in the southern hemisphere. That's the Coriolis force. So it's a little bit of a weird concept. Everything in the northern hemisphere is deflected to the left, to the right. Everything in the southern hemisphere is deflected to the left. Here's an animation. Let's try this out. Coriolis effect north to south. This is how it would go if the Earth was not rotating. Your plane or your rocket would just go straight down. But that's not reality. Reality is, now watch this, as your airplane or your rocket is airborne, the Earth, if you will, rotates underneath it. And the result of all of that is that the path of this airplane is deflected to the right relative to its sense of motion. Pretty wild. So, now in terms of wind, you have to combine the pressure gradient force and the Coriolis force. Here's the story. The pressure gradient force sets the air in motion, basically kicks the wind in the butt and says, you go. The wind now says, all right, I'm going to just go down the pressure gradient perpendicular to the isobars, because that's what the pressure gradient force tells the wind to do. However, as the wind starts to blow down the pressure gradient, it gets deflected by the Coriolis force. And it gets deflected to the right in the northern hemisphere and to the left in the southern hemisphere. So, wind direction is a combination of these two forces acting onto the moving air. So if we want to really understand how wind blows and wind direction, we have to account for both the pressure gradient force and the Coriolis force. Let's try that. Right? This is on page 100. Here we have a high pressure cell, basically a hill, if you will, of air. Here we have a hole of air. If there were only the pressure gradient force, air would simply flow down the pressure gradient from high pressure to low pressure, going across the isobars at a 90-degree angle. It would flow down the hill perpendicular to the isobars. That'd be great. But unfortunately, the Earth rotates. Well, rather fortunately, the Earth rotates, because otherwise we wouldn't have day and night. And because the Earth rotates, we get the Coriolis force. So as that wind is doing its thing and going down the pressure gradient, it's being deflected. It's being deflected to the right in the northern hemisphere, to the left in the southern hemisphere. And if you combine the pressure gradient force and the Coriolis force, winds end up blowing parallel to the isobars. And that's exactly what happens in the upper atmosphere. If you go into the upper atmosphere, if you go up above about 5,000 feet, winds always blow parallel to the isobars, because the pressure gradient force combines with the Coriolis force. This diagram and explanation is on page 100 in your book. That's what we call a geostrophic wind. Winds that blow parallel to the isobars. That's exactly what happens, again, as soon as you go above about 5,000 feet all across the planet. So it's actually quite simple if you just want to memorize it. In the upper atmosphere, winds blow parallel to the isobars. We call that a geostrophic wind. And we call that the jet stream. We'll get into that in just a second. So have a look at page 100. Have a look at this diagram if this is a little bit confusing to you. Let's look at the weather map. Here's a weather map, right? And what we have on this weather map, again, it shows us where the high pressure is located, shows us where the low pressure is located. And these black lines are the isobars. And I'm going to pose the question to you now, where's the jet stream? Where we are in the upper atmosphere now, we are maybe 20,000 feet, 30,000 feet, 40,000 feet in the sky. What's the wind direction? Remember, wind direction has to be parallel to the isobars. So here it is. It is really not all that complicated, because the only direction the wind can blow is parallel to the isobars. The wind cannot blow across the isobars. That's physically impossible. It has to blow parallel to the isobars. So in this particular case, on this particular day, this was the wind direction in the upper atmosphere across the United States. The wind cannot blow across the isobars because we have the combination of the Coriolis force and the pressure gradient force. So all you got to do is draw like a line that is parallel to the isobars. And bam, you've predicted wind direction. Here's an animation. Right, this would be the wind direction if all we had was the pressure gradient. Winds would blow from high pressure to low pressure, straight down the pressure gradient, crossing the isobars at a 90-degree angle. However, the Earth rotates, and because the Earth rotates, we get Coriolis deflection. Northern hemisphere, Coriolis deflections to the right. So let's see what happens in the upper atmosphere. See how the wind is deflected to the right. Eventually, Coriolis force and pressure gradient force combine. Winds blow parallel to the isobars. Let's try this once more. Wind goes, gets deflected to the right, and ends up blowing parallel to the isobars. These animations come on the CD that's included with your book, so you can have a look at those yourself. So, here's the story in the upper atmosphere. Upper atmosphere, again, that's as soon as you get above about 5,000, 8,000 feet. Two competing forces to deal with, the pressure gradient force and the Coriolis force. The pressure gradient force wants the wind to blow perpendicular across the isobars, following the pressure gradient. The Coriolis force says, I'm not going to allow you to do that. I'm going to constantly deflect you to the right in the northern hemisphere, or to the left in the southern hemisphere. So the wind just says, all right, whatever, I'll just do what both of you want me to do. And the only way I can do this, the only way I can make both of you happy, is to blow parallel to the isobars. And that's what the wind does in the upper atmosphere. Haha, and we have to add one more twist to this. In the lower atmosphere, if you're close to the ground, you have friction. We have to add a third force. Right? So, we have covered the pressure gradient force, we have covered the Coriolis force, and now we'll add the friction force to that. And then we have the whole story. Okay? So we'll see you in part 3.